The last time that we were together, we introduced the notion of a homomorphism, which is a function from one group to another that preserves the operation. Now, we noted that this was distinct from an isomorphism inasmuch as the definition of a homomorphism fails to include the requirement of bijectivity, right? So a homomorphism preserves the operation, but is not necessarily one-to-one nor onto. We gave an example of a homomorphism that took Z8 to Z4. And I'd like to look again at that example. So we represented Z8 as the rotations of an octagon. So if I focus on the numbered vertices here, a rotation that sends vertex 1 to vertex 2, vertex 2 to vertex 3, and so on, generates the rest of the rotations, right? So that is giving us a group, an 8-element group that is cyclic. So this is isomorphic to Z8, right? But we compared that to, now let's focus on the letters. While we're permuting the numbers 1 through 8, we're also permuting the letters A, B, C, and D. So this rotation that sent 1 to 2 also sends A to B. It sends, if I do 2 of them, A got sent to C. If I do 3 of them, A gets sent to what was position D. But after 4 of these rotations, A goes back to itself. A goes back to position A. And so this, let's see, so let's start back at the beginning again. This one rotation, that generates the rest of the elements of the group. Right? So that rotation took A to B, B to C, and so on. But once we get back to here, the identity, we continue again, right? So we wind up with a group of permutations that is isomorphic to Z4. And so the homomorphism that we are defining is the one that's going to send, well, let's see, it's going to send the identity element of Z8 to the identity element of Z4. It's going to send the function that's function that's sending 1 to 2, 2 to 3, and so on, to the function that sends A to B, B to C, and so on, and we continue like that. Now, in this way, by studying this homomorphism, what we're actually doing is ignoring some of the structure of Z8 and focusing on part of the structure of Z8, the part that is described by Z4. In particular, we can think of, let's imagine lines going from diametrically opposed vertices, and every motion, every element of Z8 permutes one of these lines into another. And so this homomorphism that we've described, in a sense, forgets about some of the structure of Z8 and focuses on that aspect that permutes lines, right? So line 1, the line connecting the A's, gets transformed by one rotation into the line that would have been connecting the B's, right? That line is the line that would have been connecting the B's originally, and so on. And this is a characteristic of homomorphisms in general. Homomorphisms allow us to forget about part of the structure of a group and focus on some aspect of the group that may be of interest to us, something that we want to study in particular. I have another example to illustrate that. You'll recognize the Rubiks Cube. And let's say I wanted to focus only on what was happening with the corner cubes and forget about or ignore what's happening with the centers, right, and with the edges. Well, I could do that algebraically by defining a homomorphism that takes, well, let's see. It would take, I'm going to think of, in its solved state, I'm going to think of that as the identity permutation of the cubes. And I'm going to send that to the solved state of the corners, the identity permutation of the corners. But I'm also going to, my function, my homomorphism is also going to take any other combination that would leave these cubies in exactly their position, but perhaps permute some of the others. It's going to send that to the identity permutation also. The identity permutation meaning the solved state of the corners. And then for every other motion of the cube, so this one, for example, right? Any other combination, any other permutation of the cubies that put the corner cubes in these positions, they would all get sent to that permutation of the corner cubies. And so in that way, what we're really doing, this homomorphism, is ignoring some of the structure of the Rubiks Cube and focusing on only the corner pieces of the Rubiks Cube. It's ignoring what's happening to everything else and focusing only on this. So by taking a homomorphism from the full cube group to the group of corner cubies allows me to basically turn this puzzle into this one. Let me give you another example. Let's take the set of integers for a moment, all the integers, and I'm going to define a function from the set of integers to the set of elements in Z2. And I'm going to do it this way. I'm going to send all the even numbers, I'm going to send those all to 0. And I'm going to send all of the odd numbers to 1. Right? And right, so there's my homomorphism. I'm sending all of the even numbers to 0, all of the odd numbers to 1. I claim that's a homomorphism. I claim that the operation on Z, and I'm assuming ordinary addition on Z, I'm assuming mod 2 addition on Z2, that the operation of ordinary addition is preserved by this homomorphism. Well, let's just check that out for a moment. So H, let's see, if I took a couple of even numbers and added them together, so call them E1, E2, let's see, what's that going to be? Well, if I add 2 even numbers, I'm going to get an even number. And so H is going to take that even number that I get whenever I add those two together. That's taking the even numbers to 0, so it's going to take that to 0. But it's also going to take, let's see, if I looked at what h did to E1 and E2 individually first, and then added them together in Z2, well, let's see, h takes E1 to 0, takes E2 to 0, and whenever I add 0 to itself in Z2, I get 0. The operation is preserved. I get the same thing whether I add first and then look at the functional value, or look at the functional values first and then do my addition in Z2. This would have worked just as well if I had used odd numbers. I'm going to use D for odd so it doesn't look like a 0. Right? So let's see. I would get, if I add two odd numbers, well, I get an even number, so I'm going to get 0. But if I took h of D1 and added it to h of D2, well, D1 is odd, so h is going to take it to 1. D2 is odd, so h is going to take it to 1. But if I add 1 and 1 together in mod 2 arithmetic, I get 0. So I get the same thing there as well. And if I had taken an even number and added it to an odd, well, let's see, even plus odd is odd. H is going to take that to 1, but it's going to take h of E to 0. It's going to take h of D to 1. And it's going to add those together, and I'm going to get 1. And by commutativity, h of D plus E is going to do the same thing, right? So h does in fact preserve the operation. Now, as I just said, homomorphisms allow us to forget some aspect of the group and focus on part of the structure that is of interest to us. And so what this particular homomorphism does is it's, well, basically forgets everything except the parity of the integer, whether it's even or odd. And it focuses on that aspect of the integers while disregarding everything else, right? So there are 3 different examples of homomorphisms. The example of Z8 going to Z4, the example of the Rubiks Cube group, the full Rubiks Cube group going to that smaller Rubiks Cube group, and taking the set of all integers and sending them to the set that contains only 0 and 1. In each case, the homomorphism allowed us to forget about some aspect of the group and focus on some aspect that we wanted that we might have wanted to study. Okay, I want to go back to our octagon group, actually our pair of groups, the pair Z8 and Z4, and I actually like to extend that just a little bit. I asked you in the last video as a homework exercise to extend that definition to include not just Z8, but Z8 cross Z2, and also Z4 cross Z2. And I asked you to extend the homomorphism that we had defined. Let's see. This was the way we defined the homomorphism from Z8, and I'm using the rotations in order to identify those elements, to Z4, and I'm using permutations of A, B, C, and D to identify those elements. Extend it to the additional elements I get by introducing a flip into it, and by flip I mean this motion right here, one that sends 1 to 8, 2 to 7, and so on. So here's my work showing that extension. In fact, what you're looking at is the completion of my completion of the homework assignment that I had given you. Down here, we have evidence that this function does in fact preserve the operation, right? If I applied f to the combination of R2 and R3f, and again, we're thinking of these as permutations, so we're reading them from, we're performing the operations from right to left. F is going to send this composition to BD, but if I looked at what F did individually to each of those elements first, I also get BD, and so on. So this works for the entire group. This might make it a little bit clearer as to what it was or how it was I was defining that homomorphism. So here we go. What this shows is that the identity element in Z8 cross Z2 was mapped to the identity element in Z4 cross Z2, but the element R4, in other words, 4 rotations, also gets sent to A. I'll show you that here again, right? So the identity element got sent to A, but 4 rotations also got sent to A. If I wanted to give you a visual here, it would be this. So if I did 4 rotations, then that goes to the identity in Z4, right? So it gets sent to the identity. It also is showing me, let's see, let's just pick on a couple of these. Let's see. So it sends R5F to BD, but it also sends, let's see, what else gets sent to BD? It sends RF to BD. So where's BD? There it is. And sure enough, I have RF and R5F both being sent to BD. So this is just another way of looking at the definition of my function. But it's an interesting way of looking at it because it may remind you of another structure that we had studied some time ago. And here, let me put a couple of ornaments on here to illustrate what I'm trying to say. So I'm going to put those 2 elements together in a set. I'm going to put these 2 elements together in a set, and so on. I'm going to do that with all of these pairs. And I'm doing that to make them look like subsets of Z8 cross Z2. And in fact, those subsets, let's see, they all have the same number of elements in them. They all have 2 elements in them. This one in particular, so this one is the one that has the identity element in it. If you examine these a little bit, I'm going to call this H. Right? If you examine each of these, I think what you'll find is that they all turn out to be cosets of this set right here. And in fact, you'll notice that this set is in fact a group. This is, well, it's certainly a subset of Z8, but it's also closed. It's closed with respect to the operation. If I did 4 rotations and another 4 rotations, I'm going to have the identity. If I do 4 rotations in the identity, I get 4 rotations, and so on. Any combination of these is again in here, so H is closed with respect to the operation, so it is a subgroup. A little bit more investigation will show you that this is a normal subgroup of Z8 cross Z2, right? So we know a couple of things now. So given that H really is a normal subgroup of Z4 cross Z2, we know that Z8 cross Z2, if I factor out H, I know that this gives me a group, right? And these are the elements of that group, right? The cosets are the elements of that group. Well, just by the fact that I was able to arrange these cosets on top of the Cayley graph of Z4 cross Z2, well, that tells me a couple of things. Well, notice none of these are duplicated, right? Each of these cosets is distinct. And so any two elements, any two cosets are going to distinct elements of Z4 cross Z2. So this function is in fact one-to-one, the one that's sending cosets to elements of Z2. In fact, let me make that clear. So I want to talk about a function f that sends Z8 cross Z2, factor out H, to my Z4 cross Z2 group, right? And I'm defining it exactly like this. So I'm sending this coset to that element. I'm sending this coset to that element, this coset to that element, and so on. So in essence, what I'm doing is I'm sending, let's see, so the elements in here look like, well, they're a coset of H, so I'll write it as XH. And where am I sending XH? Let's see. So I'm sending, for instance, I'm sending R3F to AC. How are those related? Well, AC was the image under the homomorphism that I defined between Z8 cross Z2 and Z4 cross Z2. So that was actually, so if I let H be the name of the homomorphism, then I'm sending this coset to the image under H. I know this is an isomorphism. Why? Again, any two distinct elements of my factor group, my quotient group, go to distinct elements of Z4 cross Z2. So it's one-to-one. Every element of Z4 cross Z2 has something assigned to it, right? There's a coset that's mapping to it. And so this function is surjective. And the operation is preserved. I know that because I was able to use the same Cayley graph in order to represent my group of cosets. So F turns out to be an isomorphism. Right? An isomorphism between the factor group, the quotient group, and Z4 cross Z2. Let's go back again to our homomorphism between Z and Z2. I want to ask you to do a few exercises with respect to this, and then with respect to this example, and then I would like you to do one additional problem of a more general nature. So we're using the homomorphism that we defined. First thing I'd like you to do is I'd like you to show that the elements of Z that are mapped to the identity element, in other words, the identity element of Z2, that would be 0, but there's a good reason why I'm using the language that I'm using here in this question. So show that the elements of Z that are mapped to the identity element form a group, right? So I want you to verify that the set of elements, that would be the even numbers, wouldn't it? That the elements that are being sent to the identity element, being sent to 0, form a group, and that would be then a subgroup of Z. And then I want you to prove that that subgroup is normal, right? To put that in perspective, that's exactly what happened here, right? The elements that got sent to the identity element in our example that we studied turned out to form a normal group. I want you to show that that happens in this example as well. All right, after that, let's let K denote that subgroup from part 1. In other words, K is going to be the set of even numbers, the set of even integers. And I want you to find an isomorphism that takes the factor group, the quotient group, Z mod K, to Z2. Right? A specific isomorphism. I want you to tell me where everything goes. And then I want you to do one more thing. I want you to prove for me that if I have a homomorphism between two groups, and I consider that set of elements that H maps to the identity element, and that would be, of course, to the identity element of G2, right? Because H is mapping to something. It's mapping into G2, so I must be talking about the identity element from that group. I want you to prove that that set of elements forms a normal subgroup. And that would be a normal subgroup of G1, right? Because I'm looking at all the elements of G1 that get mapped to the identity element. I want you to show that that first of all forms a subgroup of G1, but also turns out to form a normal subgroup of G1. And so in that way, again, with respect to our earlier example, I'm trying to ask you to show me, I'm asking you to show me that this set of elements that got sent to the identity element always turns out to be not only a subgroup, but a normal subgroup of our domain group that we began with. This was a challenging video. Let's meet soon and talk about some of these ideas, and we'll try to answer any questions that you might have. Please do those 3 homework exercises. I will do them as well. We'll compare answers. And until our next video, I hope that you will stay well, stay safe, and take care. So long.